Hey guys, my name is Adrian and welcome to Organic Chemistry 1 Part 3 of these recorded sessions. Today we'll be going over, for most of y'all, Chapter 3, or in general, organic molecules and functional groups. So today our topics are functional groups. I've divided them into two, so it'll be easier for you guys to navigate. Um, and then after that, physical properties, boiling points, melting points, probably the most important thing for each functional group, right? And then solubility, again, a physical property, and then just a little introduction of ionophores, so what they do, why they're important, things like that. Okay, so let's get started with the functional groups. So we'll start with the first one. So obviously, functional groups are groups, right? They're in groups for a reason, because as a group, they do something that no other group does, right? Or they contain something that no other group does. Um, they look like um, they look like a certain thing that no other group looks like, right? So for functional groups, properties such as chemical, boiling point, things like that, properties depend on what functional group you are. So we have properties, and then most importantly, with those properties, they determine either the geometry, right? So like SB1, SB2, um, hybridization, what shape it is, things like that. Or and then the most important thing for these is the reactivity, right? So is it are there nucleophilic sites, electrophilic sites? There's an oxygen somewhere in this functional group. So what's that doing to the molecule, right? What's it doing to the rest of the molecules around it, or atoms, right? So for these, we're looking for sites, right? And we'll definitely be paying attention to that as we get further along in the lessons, right? And then other than that, there's also just you know getting kind of acquainted with vocabulary. So we have aliphatic hydrocarbons, carbons, right? And we know what hydrocarbons are. Anything that's just made out of hydrogens and carbons, right? So in this case, alkanes, alkenes, and alkynes, right? And these are also special because they're open chains, right? So they're not cyclic or closed, right? So open, compared to versus the aromatic hydrocarbons, right? Which are closed, like benzene, um, cyclomolecules, things like that. So, and they're called aromatic because they have they smell, right? They smell. Um, they're cyclic, right? And that's pretty much it. The most common aromatic that we'll see is probably going to be benzene, right? And I think you've seen that probably a couple lessons ago, or if not, we'll be seeing a lot of it later on. Okay, so pretty simple. It makes sense why things are what they are, right? Why functional groups exist, because we need to determine why they're important. And it's easier to break, especially molecules get big, right? Molecules get big, and it's easier to kind of break down each section of it. This thing has this group, so we know that there's these sides. The geometry is going to be this, things like that. So let me erase this and let's do some practice with it. Okay, functional groups. So first question: why do heteroatoms confer reactivity? So we didn't really specify this in the other one, but I want to know what you guys think. So just list as many things as you can, or what you can think of, and then we'll get back to it. Okay. And then same thing, we asked about heteroatoms, and now let's do why do pi bonds? Why do pi bonds confer reactivity? And this all ties into functional groups because functional groups can have heteroatoms, they can have pi bonds, you know, so it's not just about carbons and hydrogens now, right? And then last but not least, and this one's always a good question because it always kind of tricks students, even though it's not really that you know complicated. It's just a different way of thinking. So which are aliphatic hydrocarbons? So between these, CH2OH. Okay, so take a minute, pause the video, and then we'll get back to it. Okay, so finished. So this is what I got. Let me change the color. Why do heteroatoms confer reactivity? Well, if you think about it, they contain lone pairs, right? And the most, probably the most, I guess, common example of that is oxygen. It has what, like two lone pairs, right? And also they are electron deficient, some of them, right? Electron deficiency. Okay, I think I spelled that wrong, but okay, electron deficiency, electron rich, pretty much ions, right? They can have ions um, more than others, and more importantly, with electron, they can be electronegative, just as with oxygen, right? So all those things matter in functional groups because that what that's what makes it different, right? That's what make them different from each other, right? So, and same thing with pi bonds, but this one's um, kind of more simple with than heteroatoms because heteroatoms are everything, but pi bonds are just pi bonds, right? They're reactive because they're easier to break, right? And this goes back to looking back with resonance, right? Pi bonds are just electrons, right? They're just electrons, and we can move them, right? We can shift them, and pretty much everything stays the same except for that pi bond. That pi bond can be replaced, moved. It's replaceable, right? It's kind of sad, but pi bonds are, you know, it's okay if they're gone. It's okay if they get replaced, right? So think of it that way. And then which one are aliphatic hydrocarbons? What do you guys get? I got these two, and right off the bat, why can we cross out these two we didn't circle? Because these aren't hydrocarbons, right? There's an oxygen here, which is not a hydrocarbon. There's an oxygen here, which is not a hydrocarbon. And here, these are all straight chains, right? No closed rings. In fact, if we draw this one as a skeletal structure, which we should be able to do, right? Convert them. It's just literally a line, right? The carbon here, the carbon there. And then this one is just two lines, right? The carbon here, the carbon here. So they're straight chain, no rings, no cyclic or anything like that, no heteroatom. So that's why these two are the only aliphatic hydrocarbons. So not too bad, right? Not too bad. Let's move on to I think, where it starts getting interesting, where it starts getting fun for um, organic chemistry. Functional groups 2. And this is just how I did my breakdown of these functional groups. Feel free to do your own, but these are separated by, again, from carbon heteroatom bonds to carbon oxygen carbonyl groups. So that's how I did mine. but it's always better to do your own, or even if you have the same format as I do, just rewrite them anyway. But this is how I did mine, and it's probably not going to fit in the one page. So first, let's do functional groups 2, and this one's going to be carbon to heteroatom bonding. And this is where we start seeing the R's, right? R this, R that, R groups. And that's just saying um, we like to call it the carbon cabbage, right? Because it can be anything. It can be a long chain, it can be a cyclic something, it can be, um, you know, whatever. But as long as the main part is there, it's going to be that functional group. So we have a couple. We have alkyl halides, and you've seen these already. Alcohols, I think we've seen these before as well. Ethers, amines, and diols. We don't see this a lot, but you kind of see them in biochem, so kind of introducing that. And sulfide. So how I did mine is I use R, right, which is pretty much anything. So for alkyl halides, R, and then halides, halogens, right? So that's the general structure of alkyl halides, right? So this could be a long molecule, a chain that goes on forever, but as long as it has a halogen right there, it's an alkyl halide, right? And alcohols, you guys probably already know, OH, right? And again, that R group can be anything. Ethers, OR, right? As long as there's an oxygen between R groups, that's an ether. And these could be, again, the R groups can be as big or as small as they want, right? They could be just one carbon um, big, or like 100 carbons long, right? Okay, amines. There's three different ways to kind of regular structure for amines, but um, R and H2, or R2 and H, and then R3 N, right? So pretty much the same thing, just as long as we have nitrogen, right? Um, and again, with these, they're carbon to heteroatoms, and they're all single bonds, right? We'll see double bonds later with the next functional group, set of functional groups. For thiols are SH, and for sulfides, like ethers, are SR, right? So we don't really mess around with thiols or sulfides that much, but these are the bulk of it, right? And they're all single bonds, things like that. So that's how I did mine. They're pretty. You get used to them super quick. These are probably the easiest things in OChem, right? Knowing all these, and then we'll practice with finding them in actual big molecules. So that'll be fun. Okay, so let's move on to the carbonyl groups. So you'll see carbonyl groups a lot, and they're probably going to be, yeah, they're pretty much the main thing to look out for, and even in OChem too. So carbon, oxygen, carbonyl groups, right? And then we have, again, aldehyde. Oh, not again, I mean, just the groups, right? Aldehyde, ketone, carboxylic acid, ester, amide, and you notice that there was an amide before, right? And then acid chloride. Okay. So again, I did the same thing. Um, their rec- their structures. So we have this, and then double bonds right there, right? The double bond O with the H here, and then ketones pretty similar, but this time it's gonna be an R group, right? And then carboxylic acid, I'm like running out of with OH. Oh, let me add the lone pairs because lone pairs are important, right? Esters, pretty similar to ethers, and actually a lot of people get confused between them, especially when they're in bigger molecules. So we'll see that later. I think I have some that are like that. And then amide, RN here. And this H2, or it can be R groups, right? Or one of each, H and then R. So kind of like the same format as the amide, but this time it has a carbonyl group, right? And then acid chlorides. Ooh, okay, barely made it. Okay, so these are the general structures, right? Acid chlorides, you can kind of see here how it kind of combined carboxylic acids, right? With but instead of carboxylic acid, it's a chlorine, so acid chloride. So excuse me. So you'll see things like that kind of start merging, but it's not gonna happen a lot, or actually it's gonna be with acid chloride. So you know, just you just have to know these, like the back of your hand, right? And kind of like point them out pretty much automatically, and you will be able to do that, you know, with practice. And after this, I'm pretty sure you already got it. So let's do a couple of problems. So, and hopefully they fit in one page. Functional groups two. Okay, so let's see this one. And also, I forgot to mention that rings and double bonds, triple bonds are also considered functional groups, right? And a lot of students get confused by that because, you know, they don't really have a name. That like it's not an aldehyde or an amine or things like that. But again, going back to the functional groups one, right? They have the properties, they have the geometry, which we practiced on with SP1, SP2. Um, and they have, they make electrophilic, nucleophilic sites, as we saw last lesson, right? So they're functional groups, right? But we don't really point them out because um, it's a given, it's a given. But just if someone asks you if they are, say yes. Okay, maybe I should have drawn smaller molecules, but this makes it more fun. Okay, just a couple molecules, so I want to make sure there's room for all of them. Okay, so this is one of them. So for these, we're labeling the functional groups, right? So go ahead and label while I draw the next one. You guys will probably have these done before I finish this second drawing. Okay. And you can kind of see, you notice with these um, how you kind of start seeing the different properties and stuff like that. Okay, last one. This one's the biggest molecule. Okay. And of course, you can always, you know, use the molecules from your book or even find random ones online and just kind of start doing them. Um, if you're into that again, right? Okay, so these are molecules. Take a minute, pause the video, look for them. Okay, so let me go in with my coloring and let's see what we have here. So what do you get? How many did you guys get? What did you guys get? So again, pointing out, there's an aromatic here, right? A ring, aromatic. So those are given, right? I'm not even going to label the other ones because aromatic, aromatic. And what else? These two, you should have gone as ether, right? And why is that? Because this is an R group, CH3. There's an O in the middle, and then another R group, right? And that's what I'm talking about with the R groups. They can be anything, right? Okay. What about this one? Ketone. Okay. Um, this one, amine. And that's it. That's all I have for this one. What about for this one? I got aromatic again, right? Oh, I could do this. Cool. Okay. Convenient. Okay. Another ether, right? And I guess this one's more obvious because this one's an R group, this one's an R group, right? What about this one? Another amine, right? Are we missing anything? Right. So this one, and now this one is one whole one, right? It's an amide, right? Because double bonded and H2, right? And I literally just like this popped up into my head like last semester after like 2 years of teaching, but the way kind of like I the way I kind of differentiate with amine and amide. Amine, as in single bond, right? Because we know amides have the double bond. So amine single because of the N, right? So if that works out for you, hopefully that helps. But a lot of students confuse amine and amide, so I think that's neat. And I figured out 2 years after, right? Okay. So next, this one again we have aromatic. Aromatic. Let's see what else we have. We have here an ester, right? Because oxygen double bonded to with double bonded carbonyl, right? What about this one? An amide, right? And for these, pay attention to the adjacent, right? And what about this one? And actually, like this one, this nitrogen adjacent to a carbonyl group, right? This nitrogen is adjacent to an R group. This one, right? So that's not an amide; it's an amine, right? So little things like that. And then, of course, this one, carboxylic acid, carb acid, all right? So things like that. Not too crazy. It gets really tedious, but fun at the same time because your friends who aren't in sciences or in OChem probably have no clue. So it's kind of a cool way to sound smart and draw random molecules all over the place, big molecules, things like that. So, okay, so let's go to our next topic. We have the boiling points, right? And again, same with solubility. These will keep coming up because the way the chapters are set up, it's pretty much a kind of like an overview of each functional group type thing. So, like one chapter is going to be about carboxylic acid, another chapter is going to be um, you know, carbonyls. So, like I said, they're all functional groups. They have their own boiling points, melting points, um, solubility, and what makes them unique, pretty much, right? Boiling and melting point. So this is one of those that you know you shouldn't forget. But once you once you get that concept of it, it makes sense. It's like, oh duh, you know. Okay. Before we start with the actual trends and stuff, um, let's go over intermolecular forces. And kind of just not even really going over it, it's just like to remind you that these are it, right? Just a review. So we know intermolecular forces are the bonds, right? And we have van der Waals, we have dipole. I feel like I said that funny. Dipole, um, hydrogen, um, and then ion, right? And then obviously this goes from weak to strong. So stronger down, right? So keeping this in mind, right? Before we even get to the trends, would your boiling point, just think about it, would your boiling point be higher if you have stronger bonds or weaker bonds? And that makes sense, right? If you have stronger bonds, obviously the boiling point is going to be um, much higher because it's going to be harder to break those stronger bonds, right? And that's pretty much what a lot of students forget. We're going to be going over trends, and you know they forget this one thing, and they're all wrong. So we have the BP trend and MP trend. I feel like I should have. No, I think it's the same. Okay, so boiling point, again, stronger intermolecular forces. So intermolecular forces, higher BP, right? The higher the BP, yeah, I'll do that. So higher BP, higher intermolecular forces. So compared to something like weak bonds versus like an ionic bond. Obviously, the one with the ionic bond is going to be the one with the higher boiling point, right? And then this one, the more surface area, So if it's like a big chain compared to like a small chain, so um, you kind of see the surface area in that, and then we'll do practices to kind of visualize it more. And then this one, higher polarizability. The the more polarizable it is, so the more is it willing or not willing to give up those electrons or those hydrogens, right? So can you snatch those away or no? And that kind of relates to the um, intermolecular forces, because if it's strong, they're not going to want to give those away, right? Give those electrons away because we hug it. Okay, with melting point, same thing with the intermolecular forces, right? And you notice this is kind of going down the priority list. Okay, first look for the bonding, obviously, right? And then next, for this one, symmetry. The more symmetrical it is, the higher the melting point, right? So kind of things like that. And for both of these, um, size. The bigger the size, obviously, the higher the boiling point and melting point as well, right? So size, and that's kind of like the last ditch effort. But you want to pay attention to the bonding, and then for boiling point, surface area and polarizability, and for the melting point, symmetry, right? Okay, so let's do practice, and I feel like this will make much more sense with the practice. And again, this is how I did my little table thing, but feel free to kind of do your own, and you know, just pretty much right now we're gonna be seeing a lot of trends. So start compiling those trends, especially for the final things like that, or even just if you're planning on taking like the MCAT or the DAT or whatever, having those handy things like that. And of course, if you want to make like a printed copy, there's I'm pretty sure you can always find something online that has um what you're looking for. But I like to make my own because I'm like very specific with like I want my tables to look like this, or I want them to say this, because sometimes online they'll be missing like one little thing, and you're like, I kind of want that little thing on there just for me. So more personalized, I guess. So start thinking about that if you're shooting for med school or dental school, things like that. Okay, so let's do one. Which one of these is circle, highest, and lowest boiling point out of these? Mm, Okay, let's do one more. And same thing actually. So this is gonna be the first set, and then I'll give you another set here. Oh, I ran out of room. But this is still this is gonna be set of four. So the first set of four, find the highest and lowest BP, um, and then this set of four, and then this set of four. Actually, for this one, let's do rank from highest to lowest BP. Oh, did I do that wrong? Yeah. Okay. So there's three here. So rank these. Okay. So I'll give you about, pause the video, take a minute, and show me what you got. So let's do yellow this time. Okay. For the highest BP, what did you guys get? What was the first criteria we're looking at? The priority. Bonding, right? Which one of these have the strongest bond? Right. This is highest because of that hydrogen bond, right? NH2, right? And you might be saying all of these have hydrogen bonded to them, but hydrogen bonds are only considered hydrogen bonds when they're with fluorine, oxygen, and nitrogen, right? So, and let's make a note of that. H bonds equals fluorine, oxygen, nitrogen, right? So don't forget that as well. So CHs aren't H bonds. Let's see. Yeah. So those are actually weak bonds. They're just van der Waals because they're just so common. They're just there. They're just the most stable, the most kind of the most yeah, the most common. I don't know what I'm saying. Okay, So this is the highest. And what about the lowest BP? So what's our next criteria? They have to be a big surface area, right? So these are all have the same surface area with one, two, three, four, five, six, seven, or eight actually. Yeah, seven atoms, right? This one, two, three, four, five. So this one would be the lowest BP because it has a low surface area compared to the other ones, right? So that's kind of what you're talking about with the surface area. And it's literally just how long the chain is, right? And with the surface area, we also want to look for branches, like this one. This one branched out, right? So, you know, just because it has more atoms, one, two, three, four, five, six, seven, or if it has the same amount of atoms, it's branched, so it's not as wide or as surface area, right? So, you want to spread as much as possible to kind of thin yourself out so you can boil faster. And that's kind of like with water, boiling water, you know, if compared to like a deep bowl of water versus like a thin sheet of water, which one will boil fastest? The one with the thin sheet, right? So kind of just a little comparison for you. Okay, so let's do the next set of four. Let's do pink. Okay, so same thing, highest and lowest boiling point. I just realized I don't have anything for melting point. Oh well, it's fine. Okay, so this one you should have gone for the highest again. This one, because of the H bond, right? And you might be saying, what about this one? Well, this one, this H, they just showing it, right? But it's actually bonded to this carbon. It's not bonded to the O, right? It's bonded to this carbon, and they just put that there to show that it's what functional group is this? An aldehyde, right? So I'm kind of surprised that with a pop quiz for functional groups, but aldehyde. So they just showed the H there to show it's an aldehyde, but that H is not a hydrogen bond because it's bonded to the carbon, so we don't care about it, right? So which one of these is the lowest boiling point? You should have gone this one, and you might be asking why. They all have the same surface area: one, two, three, four, five, one, two, three, four, five, one, two, three, four, five, and so on. Well, this one has this double bond, right? And also this one has this double bond, and this one has no double bonds, and just all single bonds. So which one, again, with the stronger bond, right? So double bonds are obviously stronger than single bonds. So this is low intermolecular force. So that's why, right? Things like that. So now let's go into the ranking, and you do the same exact thing for melting point. And actually, we'll come back for the melting point for one of them just to show you the melting point. With this one, you should have gone 3, 1, 2, and Y. So again, Y is the lowest BP, and I think I kind of, yeah, I kind of switched this up, but this is supposed to be the lowest. Oh, I'm doing highest. Okay, sorry. So this is the highest to lowest. So highest boiling point to the lowest. I think I kind of, okay, hold on a second. I goofed up a bit. Let's see. So the highest boiling point, let's scratch this out. is actually which one? The highest is 1, right? Um, because again of the surface area. And then the next one, okay, the next one is gonna be 2. Ooh, that was easier fixed than okay, I had it backwards. So highest boiling point is 1 because of the surface area, and then same thing with 2. Well, these all have different surface areas, right? This says 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, right? So all about surface area for this one. Okay, so let's see. You do surface area. And now let's do one with the melting point. Let me do a color so it doesn't clash. Okay, so let's do this first set of 4. Which one of these would have the highest melting point? So I'll give you a second. Right, so this one would still be the highest melting point um, because of the H bond, right? So highest, the yellow is BP, but it's also the highest um, melting point as well. What about the second highest melting point? So out of these 4, right? So this one should have been the second one. Second for oh, melting point. Because of why? Right, because of the symmetry, right? So we don't care about the surface area for the what's it called? For melting point, we care about the symmetry. And you might be asking, but you said the size, the bigger the size, the higher the melting point and boiling point. Well, size and surface area are different, right? These are all the same size because they all have 7 atoms, right? But these have bigger surface area and this is more symmetrical. So which one are you going to choose? The more symmetrical one, right? More symmetry. Okay, so things like that. Okay, we kind of made a mess here, but you guys get the point, right? Okay, so let's go to our next one, which is solubility, which is another um, great property to definitely know because you definitely need to know kind of like why things do what they do. And again, solubility, you've been exposed to it a bunch of times, like dissolves like and all that. So, and that's actually what we'll base this on lately. And then I'm gonna do it in color just to emphasize it, like dissolves light. But now, back in high school or middle school or whatever, like dissolves like we talked about solvents, solutes, things like that, right? But now we're taking it a step further. We're talking about organic versus organic, polar versus polar, ionic versus ionic, things like that. And even later, um, acids and bases, things like that, which is pretty much polarity, right? So we'll be looking at 2 kinds today. We'll be looking at ionic compounds, oh, compounds, and organic molecules. Okay, so for ionic compounds, they're going to be soluble in water and insoluble in organic compounds, right? Insoluble. And this is kind of like in lab, you did a little separation thing, and that's kind of what's happening here. because one of them is organic, one of them is aqueous, right? And organic solvents. And then organic molecules are obviously the water the other way around, but there's one exception with this for water. So soluble inorganic, obviously. So like dissolves like, right? And this is going to be an exception. Only soluble in water, um, if contains um, basically one functional group, functional group without the S, functional group capable of H bonds um, for every 5 atoms or carbons for every 5 carbons it has. So that's kind of like confusing, right? But basically, you can't be if you're an organic molecule and you're super huge, right? But you only have like one hydrogen bond. Obviously, that's not gonna dissolve in water because that 100 hydrogen bond ain't gonna dissolve that big organic molecule, right? So basically, one hydrogen bond can dissolve for every 5 carbons the molecule has. So that's what it means. What it means. So, and you'll kind of see in examples here, kind of like what they mean by that. And we know functional groups capable of H bonds. We saw oxygens for sure, right? Alcohols, things like that. Carbonyls or nitrogens, right? The amides. So keep look out for those things, and we'll definitely practice on those. So okay, so let's do practice with solubility. Okay, actually first let's do since we did since I talked about the whole you know polar, non-polar, things like that. Let's do this. CH3, CH2, and basically you're gonna tell me if it's soluble or insoluble in um, and then same thing over here. Okay, so label the arrows if it's soluble or insoluble and why. So take a second, pause the video and come back. Okay, welcome back. So you should have gone CH2, CH3, CH3, CH2, CH2, CH3 is organic, right? So you should put here soluble because it's organic. And also another thing, um, it's polar, right? I mean non-polar. Sorry. Let's put here. Okay. And then with H2O, it's polar, insoluble. because we know this one is nonpolar, right? So like dissolves like, nonpolar to nonpolar, insoluble and polar, right? Things like that. And for this one, what is this one? This one's gonna be polar. So, and we already said this is polar. This is nonpolar. Oh, well, okay. So this one soluble here, insoluble here. So does that make sense? Polarity is also like dissolves like, right? Polar versus polar, and that's pretty much polarity is ionic. Polarity is the ionic compound. So things like that. So these are just examples. Let's get head to the actual problems, and I think these are pretty fun. You're probably thinking like, wow, you think that looks fun, but sorry. So let's try these. Okay, so label, circle the least and most soluble in H2O, and then this one. Okay, so this one is asking if it's soluble in water. Water soluble. Okay, so take a second, pause the video, come back. Okay, let's do something with purple. So least soluble, we should have gotten this one, and why? H2O we said is polar, and this is the only one that's non-polar, right? Non-polar. So it's not even going to dissolve in that. So now all of these are polar. So how do we decide which one's the most soluble? Well, which one is the most similar to water? OH, right? It has an H bond. Both of them have an H bond, so they're super similar. This one can't make an H bond, but still kind of polar. This one is polar, but it can't make an H bond. Um, well, it can, but it has to break off, which we know halogens can't have two bonds, right? So this is going to be the most soluble. And that's it. Like is always like. Easy as that. And this, we should have gone no. Because look at this. This is what I was saying. It's capable of one hydrogen bond with how many carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. One hydrogen bond for 18 carbons. That's not going to dissolve. And that just makes sense, right? This is too big to dissolve in water because there's no hydrogen bonds going on, right? So, one H bond per 18 carbons. That's a no. No, 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 no. We want five or less, right? Five or less for each H bond. So crazy, right? So solubility. The main thing to keep in mind with solubility is the polarity. A lot of people forget that polarity takes into account as well, right? Um, you know, it's easy to tell what polarity is. Polarity just follow the dipoles, where's the electronegativity coming from? So I think if you think of polarity, its solubility, it'll make your life much easier. You don't have to constantly think about Oh, like in lab. I'm pretty sure in lab you're kind of like, which one of these are organic again, or which one of these are aqueous? Well, that's just saying, which one of these are polar, which one of these are non-polar. And you can just look at the formula or the molecular formula, and you'll you got it, right? So polarity, solubility go hand in hand, right? Okay, so let's go to our next topic, and just kind of introducing it, but it's kind of fun. Ionophores. Um, this one just about crowns, pretty much. They're organic molecules um, with complex cations. Complex cations, and meaning they hold cations. Does that make sense? So, and these are important because they are hydrophobic, phobic exterior that makes them soluble. Again, solubility, right? And this will help in biochem. There's a lot of this in biochem, like steroids, whatever you have, right? Cholesterol, whatever. Soluble in the nonpolar interior of the cell membrane, right? And most important with this is the crown ethers. And this is kind of what they look like. And they're just cyclic ethers, right? Makes sense. This is kind of what they look like. This is the most simple one, right? They're all bonded, and this is where they have the little um cation complex thing. So basically, something they'll be in here, right? So the outside is nonpolar, right? So they get through, they sneak in whatever's in there, and they release it, right? So it's kind of like what drugs do. You coat them in something to kind of sneak them into somewhere, and then they release whatever's inside, right? And just another fun fact, you name these as, for example, this one is named 12 crown 4. 12 for how many atoms it has. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 12 atoms, and then 4 for the oxygen. So 1, 2, 3, 4 oxygens. So that's how you name crowns. O2. Okay, so with that being said, that's our last topic. Thank you guys for watching. Um, you know, again, these are the topics we covered. Definitely skip around, or obviously if you're at the end, you already watched it. But thank you guys for joining me, and hopefully I'll see you again next time. Thank you guys. Bye.